Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through the quiet immensity of space, through the birth and death of stars, the long silence between galaxies, the strange warmth at the edge of a black hole, and the deep questions that have followed physics like a shadow across half a century of thought. There is no urgency here. There is only the slow passage from one idea to the next, the way starlight moves through space, steady, unhurried, carrying what it carries from distances that have no easy analogy. These ideas can arrive the way stars appear on a clear night, not all at once, one by one, out of the darkness, until the whole sky is present. There is a kind of attention that comes naturally when you stand outside on a clear night and your sight adjusts. It is not the sharp focus of concentration. It is something softer, a widening, a settling. The surrounding world falls away at the edges. The sky, which had seemed merely dark, begins to fill. The stars that appear are not close. Even the nearest ones, beyond our own sun, are so far away that the light reaching your eyes left its source years before this moment. Some of the stars you can see without instruments sent their light 1,000 years ago. A few are farther still, thousands of years in travel. When you look up at a clear sky, you are not seeing the universe as it is tonight. You are seeing the universe as it was at dozens of different moments, all arriving simultaneously, all landing in the same quiet eye. This is the first and strangest thing about light. It travels faster than anything else we know of, nearly 300,000 kilometers per second. And yet the universe is so vast that light still takes time. The Andromeda Galaxy, our nearest large neighbor, is 2.5 million light-years away. The light it sends reaches us 2.5 million years after it was released. That light was already traveling when the first humans were learning to shape stone. When you look at Andromeda on a dark, clear night, visible to the unaided eye as a faint smudge in the constellation of Andromeda, you are looking at a moment that predates our species by an enormous margin. That is not a metaphor. That is simply the geometry of the place we live. The universe is, in this sense, always showing us its past. There is no way to see the cosmos as it is right now. Every glance outward is a glance backward through time. Look a little farther, and the past grows deeper. Look as far as instruments can reach, and you are seeing light from a time when the universe itself was barely a few 100,000 years old. That ancient light, the oldest light we can observe, is called the cosmic microwave background. It arrives from every direction equally, a faint and uniform glow of radiation that fills the universe completely. It is the afterglow of an era when the cosmos was so dense and so hot that it was opaque, a luminous fog through which no photon could travel freely. Then, as the universe expanded and cooled, that fog lifted. For the first time, light could travel across open space. The photons that were released at that moment have been traveling ever since, cooling, stretching, their wavelengths lengthening from visible light into microwave frequencies, and they reach our instruments today as a remnant warmth of about 2 7/10 degrees above absolute zero. Satellites have mapped this ancient light across the entire sky with extraordinary precision. And in its faint variations, temperature differences of roughly 1 part in 100,000, they have found the seeds of everything that ever grew in the universe. The cosmic web of filaments and voids, the clusters of galaxies, the galaxies themselves, the stars within them, and the planets around those stars. All of it traces back to small fluctuations in density imprinted on that first light, amplified by gravity over 13 billion years into the structures we inhabit now. We will return to some of these structures. But first, let us begin a little closer to home. Our own solar system contains 8 planets, dozens of significant moons, and an uncountable number of smaller objects arranged into belts and clouds across a span of space so wide that the fastest spacecraft ever built would take tens of thousands of years to cross it completely. The inner planets, Mercury, Venus, Earth, and Mars, are rocky and relatively small, each shaped by its particular distance from the Sun and by the accidents of its formation. Mercury, closest to the Sun, has almost no atmosphere. Its surface is marked by craters that have remained unchanged for billions of years because there is no weather to erode them and no geology to resurface them. Its days are extraordinarily long, and in the absence of any insulating atmosphere, temperatures swing from several hundred degrees in sunlight to hundreds of degrees below zero in shadow. Venus is nearly the same size as Earth and might once have been quite similar. But something went wrong, or rather, something went differently, and its atmosphere thickened into a dense envelope of carbon dioxide, trapping heat and driving surface temperatures to nearly 500 degrees. Its clouds reflect so much sunlight that Venus is often the brightest object in the night sky after the moon, beautiful and brilliant, concealing a surface hostile to anything we would recognize as life. Mars holds a particular kind of melancholy. There were rivers there once, and perhaps broad, shallow oceans. Its surface still carries the marks of ancient water, dry channels, sedimentary deposits, minerals that only form when water is present. The planet's climate changed slowly over billions of years, its thin atmosphere eroding away under solar radiation, its liquid water retreating into ice at the poles or deep underground. Spacecraft have returned photographs of Martian landscapes that look in places strikingly like arid regions of Earth, red rock and dust, the shapes of erosion, the quiet geometry of ancient geology. Except no wind carries any sound there, except nothing alive has walked that surface for a very long time, if anything ever did. Beyond Mars, across the asteroid belt, the scale of the solar system changes dramatically. Jupiter is a world that dwarfs everything around it. It contains more than twice the combined mass of all the other planets. Its surface, or rather the top of its deep and continuous atmosphere, is banded with storms, with chemical gradients, with the play of pressure and temperature across a sphere more than 11 times the diameter of Earth. The Great Red Spot, a storm system that has been rotating since before the invention of the telescope, is larger than our entire planet and still not fully understood. Jupiter's 4 largest moons are worlds in their own right. Io, the innermost, is the most volcanically active body in the solar system, its interior heated by the tidal flexing of Jupiter's immense gravity. Europa hides a liquid water ocean beneath a shell of ice, an ocean that may contain more water than all of Earth's oceans combined, in contact with a rocky sea floor where chemistry might unfold. Saturn's rings are one of the most visually extraordinary structures in the solar system. A flat disk of ice and rock extending 200,000 kilometers from the planet, but averaging only about 10 meters in thickness, proportionally as thin as a sheet of paper stretched to continental scale. Those rings are geologically young, perhaps only 100 million years old, which means they were not present when the dinosaurs walked the Earth. They will not be permanent features. They are something the solar system is briefly wearing and will eventually let go. Farther out, Uranus and Neptune exist in a cold and faintly understood realm, their interiors likely made of ices and rocks surrounded by deep atmospheres of hydrogen and helium. Uranus rotates on its side, the result of some ancient collision that knocked it into an oblique spin billions of years ago. Neptune's winds are the fastest recorded in the solar system, faster than any hurricane on Earth, yet persisting not for days, but for centuries. And beyond Neptune, the Kuiper Belt extends into a dim and drifting realm of icy bodies, including Pluto, which cycles through a thin and fragile atmosphere that expands slightly when Pluto is closest to the Sun and then freezes back onto the surface as it moves away. All of this, vast as it seems, is just one solar system among hundreds of billions in the Milky Way alone. We now know of thousands of planets around other stars. Some are larger than Jupiter, some are smaller than Earth. Some orbit so close to their star that they complete a full year in a matter of days, their surfaces baked by perpetual proximity. Some receive so little light that they are perpetually frozen. A few orbit in what astronomers call the habitable zone, the range of distances at which liquid water could exist on a rocky surface. Whether those planets actually have water, or atmospheres, or life, we do not yet know. We are just beginning to read the signatures their atmospheres leave in starlight, looking for the chemical fingerprints of something familiar. The variety is humbling. The universe makes planets easily, in every conceivable configuration, and most of them we will never visit. Most of what we know, all of what we are made of, traces back to stars. A star is born from a cloud of gas and dust, mostly hydrogen, with some helium, and traces of heavier elements left behind by earlier stars that already lived and died. Over millions of years, gravity slowly gathers this material. The cloud contracts. Its center grows warm, then hot enough for nuclear fusion to begin. Hydrogen nuclei pressed together under enormous pressure and temperature fuse into helium. A small fraction of their mass is released as energy, and the cloud becomes a star. Our sun has been doing this for about 4.5 billion years. At the rate it burns, it will continue for another 5 billion. In its core, every second, 600 million tons of hydrogen are converted into helium. The energy released travels outward through the sun's interior and emerges at the surface as light and heat, crossing the roughly 150 million kilometers to Earth in about 8 minutes. When warmth falls on your skin from the sun, it began as a nuclear process at the center of a sphere, more than 1 million times the volume of the Earth, then spent 8 minutes traveling here. That connection between the warmth you feel and a process at the heart of a star is one of the most intimate facts astronomy offers. Stars are not all the same. There are red dwarfs, smaller and cooler than the sun, burning their fuel so slowly that they can persist for trillions of years. There are blue supergiants, vastly more massive, blazing so intensely that they exhaust their fuel in millions of years rather than billions. There are binary systems where two stars orbit each other in an intricate gravitational dance, sometimes so close that material streams between them. The range of stellar masses spans from about 8% of the sun's mass at the lower limit, below which fusion never ignites, and the object remains a failed star called a brown dwarf, to perhaps 200 times the sun's mass at the upper limit, where radiation pressure is so intense that the star is barely stable. When a star like our sun reaches the end of its fuel supply, it swells into a red giant, its outer layers expanding enormously while its core contracts. The expanding envelope may engulf the inner planets. Then the outer layers drift gently away into space, forming a beautiful glowing cloud called a planetary nebula, a misnomer from an earlier era, since planetary nebulae have nothing to do with planets. The core that remains is a white dwarf, a dense, hot object roughly the size of Earth, made of carbon and oxygen, slowly radiating its stored heat into space. Over billions of years, it cools. Eventually, in the very far future, it would reach a cold, dark state called a black dwarf. But no black dwarf is thought to exist yet, because the universe has not been around long enough for any white dwarf to cool that far. More massive stars end very differently. When a star several times the sun's mass exhausts its fuel, its core collapses in a fraction of a second. The collapse is so rapid and so violent that it produces a shock wave that blows the outer layers off in an explosion, a supernova, briefly visible from across an entire galaxy. In the intense conditions of this explosion, temperatures and pressures reach levels that allow the creation of elements far heavier than iron: gold, platinum, iodine, uranium. The iron in your blood was forged inside a star. The calcium in your bones was scattered by a supernova. The gold in any piece of jewelry anyone has ever worn was assembled in conditions of extreme stellar death. After the supernova, something remains. If the original star was massive enough but not too massive, the remaining core collapses into a neutron star, an object the size of a city but containing more mass than the Sun, so dense that a spoonful of its material would weigh as much as a mountain range. If the star was more massive still, the collapse continues past the neutron star state. The core becomes a region of space-time from which nothing, not even light, can escape. A black hole. In April of 2019, a collaboration of radio telescopes spread across the globe, functioning together as a single instrument the size of the Earth itself, released the first photograph ever taken of a black hole's shadow. The target was the supermassive black hole at the center of a galaxy called M87, 55 million light-years away. What appeared in the image was a glowing ring of orange and red light, heated plasma, orbiting at close to the speed of light, surrounding a central region of complete darkness. That darkness is the silhouette of the event horizon. The event horizon is not a surface in any ordinary sense. It is a boundary in space-time, a region of no return defined not by any material barrier, but by the geometry of curved space. Outside the event horizon, light can still move outward and, given enough time and distance, escape. Inside the horizon, every possible path, including the paths of light, curves inward. There is no direction that leads out. The future only ever points deeper in. For a black hole with the mass of our Sun, the event horizon would be a sphere roughly 6 kilometers across. For the black hole at M87, containing 6.5 billion solar masses, the event horizon is larger than the orbit of Neptune around our Sun. For the Milky Way's central black hole, Sagittarius A, containing 4 million solar masses, the event horizon is still smaller than the orbit of Mercury. For decades, the mathematics of black holes produced a result of striking simplicity. A black hole could be completely described by just 3 numbers: its mass, its electric charge, and the rate at which it spins. Nothing else was observable from the outside, no trace of what it had consumed, no memory of what had fallen in. A black hole formed from 1 million tons of books would be indistinguishable from one formed from 1 million tons of rock. All the structure, all the specificity, all the information about the original material apparently gone. This simplicity seemed elegant, and it carried, hidden inside it, a deep and troubling contradiction. In the early 1970s, a doctoral student at Princeton named Jacob Bekenstein was working through the thermodynamics of black holes. He noticed something that troubled him. The second law of thermodynamics, one of the most fundamental principles in physics, states that the total entropy of a closed system can never decrease. Entropy is a measure of disorder, of the dispersal of information across possible states. When something burns, entropy increases. When something falls apart, entropy increases. But if a hot object falls into a black hole and is absorbed without a trace, where does its entropy go? If the black hole carries no entropy, the entropy of the universe seems to have decreased. The second law is violated. Bekenstein proposed that black holes must carry entropy. and that this entropy must be proportional to the area of the event horizon, not to the volume of the black hole's interior, but to the area of its boundary. Each small patch of horizon, at the smallest meaningful scale of space-time, encodes one fundamental unit of information. Stephen Hawking resisted this at first. The logic of thermodynamics said that anything with entropy must also have a temperature, and anything with a temperature must radiate. But black holes did not radiate. Light fell in. Nothing came out. Bekenstein's proposal seemed to contradict the whole meaning of an event horizon. Then, late in 1973, Hawking performed a calculation that changed the picture. He applied quantum field theory, the framework that governs matter and energy at the smallest scales, to the curved space-time near a black hole's horizon. In quantum mechanics, the vacuum of empty space is not truly empty. Pairs of particles and antiparticles flicker briefly into existence and then annihilate, a consequence of the Heisenberg uncertainty principle as it applies to energy and time. This happens everywhere at all times as a fundamental feature of space itself. Near the event horizon of a black hole, something unusual can occur. One member of such a pair may fall inward while the other escapes outward. To a distant observer, the black hole appears to be emitting particles. It glows. It has a temperature. The temperature is extraordinarily small. For a black hole with the mass of our Sun, it would be roughly 60 billionths of a degree above absolute zero, far colder than the faint background radiation of the universe itself, far beyond any instrument's ability to detect. But it is not zero. And because it has a temperature, the black hole slowly radiates energy. And because it radiates energy, it very slowly loses mass. Over time, scales of extraordinary length, something on the order of 10, followed by 67 zeros years for a stellar mass black hole. The black hole would eventually evaporate entirely, dissolving into a last faint release of radiation and ceasing to exist. What Hawking could not immediately answer was what that radiation carried. In ordinary thermal glow, the light emitted by a warm object tells you its temperature and very little else. The same featureless spectrum, whether the object is made of iron or carbon or gold. His calculation gave the same answer for a black hole. The outgoing radiation carried no imprint of whatever had fallen in. When the black hole finally vanished, everything that had ever crossed its horizon seemed to vanish with it, permanently erased from reality. This was in quiet but profound conflict with quantum mechanics. Quantum mechanics has spent a century establishing one principle with no known exceptions. Information cannot be created or destroyed. It can be scrambled, dispersed, hidden in correlations so subtle that no experiment could untangle them. But it cannot be annihilated. The equations that describe how quantum systems evolve through time are reversible. Given the final state of a system, you can, in principle, reconstruct the initial one. This reversibility is called unitarity, and it is not a minor technical detail. It is one of the load-bearing walls of the theory. If a black hole evaporates by releasing purely featureless thermal radiation with no memory of what fell in, then when the black hole finally disappears, the information about everything that crossed its horizon disappears with it. A permanent erasure. Unitarity is violated. Quantum mechanics is broken. This became known as the black hole information paradox, and it ignited what physicist Leonard Susskind would later call the black hole war. On one side stood Hawking, arguing that quantum mechanics would need to be revised in the extreme context of black hole evaporation. That information loss was real. On the other stood most particle physicists, including Susskind and the Dutch physicist Gerard 't Hooft, who held that quantum mechanics was not negotiable. The rules did not have exceptions in extreme conditions. Hawking had to be missing something. If information could truly be destroyed, the implications radiated outward in ways physicists found unacceptable. Conservation laws would become approximate. The arrow of time would lose its foundation. The probabilities that quantum mechanics assigns to outcomes would no longer sum to one, a mathematical impossibility. The universe would cease to be self-consistent in a way that struck most physicists as simply not permitted. For 30 years, the paradox held. Papers were written, bets were placed, arguments continued at blackboards in physics departments around the world. Some proposed that black hole evaporation slowed and stopped at some tiny scale, leaving behind stable microscopic remnants that carried all the lost information. But if such remnants existed, quantum mechanics required they be produced in enormous quantities in any sufficiently energetic collision, and no evidence of them appeared. The paradox resisted every proposed resolution and deepened with each passing decade. Then, gradually, a new idea began to take shape. An idea that sounded at first more like a philosophical claim than a physical one. In 1993, Gerard 't Hooft proposed something that carried with it the quiet quality of the genuinely new. All the information contained within a three-dimensional region of space, he suggested, could be completely described by a theory living on the two-dimensional boundary of that region. The interior was not the most fundamental description. The interior was derived from the boundary, the way the image of a three-dimensional scene is derived from the interference patterns etched on a flat holographic plate. Leonard Susskind developed this idea into what became the holographic principle. The claim is precise and extraordinary in equal measure. The number of possible states in a region of space is bounded not by the volume of that region, but by its surface area. Each small patch of boundary, at the scale of the smallest meaningful distance in physics, encodes one fundamental bit of information. For a black hole with the mass of our Sun, the event horizon, a sphere 6 kilometers across, can store something in the neighborhood of 10, followed by 77 zeros, bits of information. Everything that has ever fallen into that black hole, every particle and photon and fragment of structure, is recorded there in the quantum texture of the boundary. In 1997, a physicist named Juan Maldacena published a paper that gave the holographic principle its first rigorous mathematical home. He showed a precise and complete equivalence between two very different-looking theories. One described a five-dimensional curved space-time containing gravity, a space with black holes and bending geometry, where all the familiar machinery of general relativity applied. The other described a four-dimensional flat boundary of that space, containing quantum particles interacting with each other, with no gravity at all. Maldacena showed that these two descriptions were, in a deep mathematical sense, the same theory. Every process in the five-dimensional interior corresponded exactly to a process on the four-dimensional boundary. The two descriptions were interchangeable. This correspondence, known as ADS-CFT, or gauge gravity duality, transformed the information paradox from an argument into a calculation. If a black hole in the gravitational interior corresponds precisely to a thermal quantum system on the boundary, and the boundary system obeys the ordinary reversible rules of quantum mechanics, then information must be preserved. The evaporation of the black hole in the interior corresponds to a unitary process in the boundary theory. Information is not lost. It cannot be, because the boundary description is running in full compliance with quantum mechanics, and the interior is derived from the boundary. The apparent disappearance of information is an artifact of viewing only the interior description and mistaking it for the whole picture. The question shifted. It was no longer whether information survived. It was how the encoding worked, and how information was eventually released. In August of 2015, Stephen Hawking stood before an audience of leading physicists at the Royal Institute of Technology in Stockholm and offered what he believed was the mechanism. He had spent more than 4 decades on this problem. The resolution he presented rested on a set of mathematical symmetries governing space-time at large distances, symmetries that had been studied decades earlier in work on gravitational waves by Hermann Bondi and others, but whose connection to the information paradox had not been fully appreciated. When a particle approaches a black hole and falls through its horizon, its gravitational field does not simply cease to exist. The horizon responds. It distorts, very slightly, in a permanent and specific way. This distortion is not random noise. It is a precise encoding of the quantum information carried by the infalling particle, written into the event horizon as a kind of gravitational memory. Hawking, working alongside Malcolm Perry from Cambridge and Andrew Strominger from Harvard, showed that these gravitational imprints were real, were mathematically well-defined, and could, in principle, store vast amounts of information. Strominger named these encodings soft hair, an echo of the old no-hair theorem and a gentle refutation of it. Black holes are not featureless. They are not without memory. The horizon carries, in its fine quantum texture, the detailed record of everything that has ever crossed it. Soft hair consists of quantum excitations, gravitons and photons, living on the surface of the horizon. They carry no energy, which is why they had been invisible in earlier analyses. But they carry information. As the black hole slowly evaporates, the outgoing Hawking radiation interacts with this soft hair. The record encoded on the horizon is gradually transferred, quantum bit by quantum bit, into the escaping particles. The information is conserved. Unitarity is preserved. Hawking offered one further observation, almost quiet in its weight. The information is preserved, but it is returned in what he called a highly scrambled form, so deeply entangled across so many degrees of freedom that no physical process could ever reconstruct the original. He described it as a library reduced to ash. The laws of physics guarantee that the information exists somewhere within the cinders, but no conceivable observer could ever recover the original volumes from them. The universe keeps its records complete. It keeps them in a language that will never be read. The success of the holographic principle in addressing the information paradox naturally raised a further question. If the event horizon of a black hole stores information on its surface, if the interior of a black hole is a holographic projection of a boundary description, then what about the boundary of the universe itself? What about the origin of time? This is the territory that Hawking turned to in his final years. The equations of general relativity, when traced backward to the Big Bang, arrive at a singularity, a point of infinite density and infinite curvature where the theory breaks down and produces no meaningful answers. This singularity is not simply a gap in our knowledge, it is a signal that the framework of classical gravity is reaching its limit. A singularity is not a physical object, It is more like a flare sent up from the heart of physics, announcing that the model has gone as far as it can go. In the early 1980s, Hawking and the American physicist Jim Hartle asked a question no one had managed to put into rigorous mathematical form before. They asked, what is the quantum state of the universe as a whole? What initial conditions does quantum mechanics actually predict for the cosmos? Their answer was the no-boundary proposal. To understand it requires setting aside one familiar assumption about time. In general relativity, time is not a fixed background. It is part of space-time itself, curved and shaped by mass and energy. Treating time as a line stretching backward to a single point is to assume it behaves like a railway track, pre-existing and independent of the universe moving along it. That assumption does not hold at the very earliest moments, when the universe was smaller than any subatomic particle and quantum effects governed everything. Hawking and Hartle replaced ordinary time, the time of clocks and calendars, with what mathematicians call imaginary time. This is a precise mathematical transformation. When the time coordinate is multiplied by the square root of -1, it stops behaving like time and starts behaving like a spatial dimension. In this imaginary time description, there is no forward, no backward, no arrow pointing from past to future. There is only geometry. In this four-dimensional imaginary time geometry, the history of the universe can be treated as a curved surface. And like the surface of a sphere, this surface is finite but unbounded. A traveler moving across the surface of a sphere never reaches an edge. They can walk in any direction indefinitely, and the surface simply continues to curve back around. There is no wall, there is no end of the world. The surface is finite in area, and yet it has no boundary. Hawking and Hartle proposed that the universe in imaginary time is precisely this: a smooth, closed, four-dimensional surface with no boundary and no edge. And the beginning, the point we would call the Big Bang, is not a singularity where physics breaks down. It is something more like the South Pole of the Earth. At the South Pole, the ordinary laws of geometry hold perfectly well. There is nothing south of it, not because a barrier blocks the way, but because the concept of south simply has no meaning there. The surface curves away, and moving outward from that point, directions begin to differentiate. The concept of north emerges, then east and west. In the same way, within the no-boundary proposal, there is no time before the Big Bang, not because the question goes unanswered, but because it gently dissolves. Before is a concept that requires a distinguished direction of time. At the smooth geometric pole of the universe's beginning, that direction has not yet emerged. The question does not demand an answer. It loses its meaning quietly at the boundary where meaning runs out. The universe, in this picture, has no external cause. It does not require some prior condition to set it going, some hand to wind it up. It is a complete, finite, boundaryless geometry. And its wave function, the quantum object that assigns probabilities to entire four-dimensional histories, contains within itself everything that the universe is and has ever been. The boundary condition of the universe is that it has no boundary. In the final years of his life, Hawking returned to this proposal together with his long-standing collaborator Thomas Hertog. They asked what would happen if the tools of holography, the mathematical framework developed from Maldaceno's work, were applied directly to the no-boundary wave function. They treated the exit from the universe's earliest inflationary phase as a boundary and described the physics there using the language of a boundary quantum field theory. The answer they found was clarifying. When you ask what kinds of universes the no-boundary wave function predicts, when you ask which four-dimensional geometries carry real probability, the holographic calculation says only the nearly smooth ones, only the nearly spherical, nearly uniform ones. The wave function strongly disfavors wildly disordered or irregular geometries. They occur with vanishingly small probability. The infinite chaotic sprawl of an eternal multiverse, a picture in which every possible universe branches off endlessly from a period of runaway inflation, turns out to be an artifact of taking the interior description too literally, of treating it as fundamental when it is not. The boundary description, the deeper and lower dimensional encoding, tells a different story. A finite universe, a smooth universe, a universe that, in its broad shape and character, resembles our own. Not one possibility among infinitely many, but a prediction. This has a further implication that takes some quiet sitting with. If the holographic principle applies not just to black holes, but to the universe as a whole, then the four-dimensional space-time we move through is not the most fundamental description. It is a projection. The primary reality, if such a phrase is meaningful, is a lower dimensional boundary theory, simpler and without gravity, from which space-time and mass and the long, slow evolution of galaxies all emerge as holographic reconstructions. Space, in this picture, is not a container in which things are placed. Space is a network of relationships, specifically, relationships of quantum entanglement between degrees of freedom on a boundary surface. The distance between two objects is a measure of how entangled the corresponding boundary states are. Creating a black hole corresponds to thermalizing a region of the boundary. Watching a galaxy drift across the sky corresponds to watching the holographic projection of quantum information in motion. The experience of depth, of distance, of the vast and silent reaches between the stars, all of it is the bulk description of processes occurring on a surface at the origin of time. This is not a claim that the universe is not real. A holographic projection is genuinely there. The stars do shine. The planets do orbit. The light does travel. But the deeper accounting, the most fundamental description of why things are the way they are, lives somewhere else, in a simpler geometry from which all of this quietly arises. The physicist Hermann Weyl, whose work on symmetry helped lay the foundations of modern physics, once wrote that the problem of space is really the problem of the relations that hold between things in space. Holography takes that insight to its logical conclusion. Space is not prior to the things within it. Space is constituted by their relationships. And those relationships are, at their deepest level, the entanglement patterns of a boundary we cannot visit. A surface not in space, but at the beginning of time. The universe is not standing still. It is expanding, and not merely expanding at a steady rate, but accelerating. Something is pushing space-time outward with increasing speed. This something, which we call dark energy, remains one of the deepest mysteries in physics. It appears to be a property of space itself. As space expands, dark energy does not thin out. It persists, and its influence grows. Currently, it makes up roughly 68% of the total energy content of the universe. Over the next several billion years, the consequences will be visible, even at the scale of galaxies. The Milky Way and the Andromeda Galaxy are currently approaching each other at about 110 kilometers per second. In roughly 4 billion years, they will begin to merge, not a collision in any violent sense, since galaxies are mostly empty space, but a slow gravitational interweaving that will rearrange the stars of both systems into a new shape, probably an elliptical galaxy, over the course of several billion more years. The Sun will not be there to see this. Long before the merger, our star will have exhausted its core hydrogen, expanded into a red giant, and eventually shed its outer layers into space. What remains will be a white dwarf slowly cooling. Earth, depending on the details of the Sun's expansion, may or may not survive in anything like its current form. Further out in time, the universe grows quieter. Stars will exhaust their fuel. New star formation will slow and eventually stop as the gas that feeds it is consumed or heated beyond the point where it can collapse. One by one, the lights of the galaxy will go out. White dwarfs will cool toward absolute zero over hundreds of billions of years. Neutron stars will continue to spin, slowing gradually, their pulses growing more faint. Black holes, fed by nothing, evaporating through Hawking radiation, will shrink over those extraordinary timescales Hawking calculated, and eventually dissolve into a final gentle release of photons and disappear. After the black holes are gone, in time scales measured in years with 30 or more zeros following, even protons, the particles that make up the nuclei of atoms, may themselves decay. Every atom of matter that the universe ever made would dissolve back into energy. Nothing of the ordinary kind would remain. What remains is a vast, expanding, cooling void, growing colder, growing more uniform. Every difference, every gradient, every concentration of energy or information smoothing out over incomprehensible time until the universe approaches a state of maximum entropy, a condition physicists call the heat death, where nothing further can happen, where every process that could extract energy has already run, and the cosmos settles into a cold, thin, nearly featureless equilibrium. It is, in its way, a kind of completion. The universe begins smooth and nearly uniform, from that gentle geometric pole at the origin of time, and it ends smooth and nearly uniform, its energy spread as evenly as physics permits across a space that has grown immeasurably vast. The no-boundary proposal suggests that this entire history, from the first moments to the last cold radiation, is itself a closed geometry, a four-dimensional surface with no beginning that requires a cause and no ending that requires an explanation. It simply is. We are somewhere in the middle of it. We are the universe briefly concentrating itself, briefly becoming aware, briefly looking back at its own structure, with questions it cannot quite answer. There are questions that physics cannot yet answer. We do not fully understand what dark energy is or why it has the value it does. We do not know the precise nature of dark matter. which shapes every large structure in the universe and constitutes another 27% of its total energy content. We do not know whether the universe extends beyond the observable horizon, whether there are regions of space-time we can never reach and will never see. We do not know whether the soft hair mechanism, as Hawking described it, is the complete resolution of the information paradox or only a partial step. We do not know whether anything lives out there in the vast reaches of the cosmos, on the ice-covered moons of our own solar system, on the planets of other stars, in some chemistry we have not yet imagined. The universe contains at least 2 trillion galaxies in the observable volume. Each contains hundreds of billions of stars. Most of those stars have planets. Whether any of those planets host something that wonders as we wonder, something that lies awake at night and thinks about stars, is one of the most extraordinary open questions in all of science. And yet, what we do know is already extraordinary. The light arriving from the farthest galaxies left those sources billions of years before the Earth existed. The calcium in bones and the iron in blood were assembled inside stars that exhausted themselves and scattered their material across space before our sun ignited. Space-time is not a fixed stage, but a dynamic geometry, rippling with gravitational waves that cross the universe, carrying records of events more extreme than anything in ordinary experience. Even the most perfectly dark places, the event horizons of black holes, which we once thought of as boundaries of absolute erasure, carry in the quiet quantum texture of their surfaces the encoded record of everything that ever crossed them. The universe remembers everything. It writes its records in a language no observer can read, on surfaces at the boundary of time, and still it remembers. There is something in that which invites a particular kind of rest. Not the rest of having found all the answers, but the rest of having let the questions be as large as they are. The cosmos is not a problem waiting to be solved. It is a place, expanding, cooling, carrying its deep structures across distances that no word quite reaches, and you are somewhere within it, briefly, made of its materials, lit by its light, breathing its chemistry in and out without thinking about it, wondering the same questions that will outlast any one lifetime and perhaps outlast the stars themselves. The night is quiet. The universe is very large, and everything that has ever been is still, in some precise and intricate way, held. End of script. Approximate spoken word count, 8,900 words. At a calm sleep narration pace of roughly 130 words per minute, this runs approximately 68 minutes of narration. Section summary for 11. Labs. Chunking. Welcome, 180 words. The night sky and the age of light, 700 words. Planets. A quiet variety, 820 words. Stars. The engines of everything, 720 words. Black holes, where gravity reaches its limit, 650 words. Hawking radiation, the warmth of darkness, 720 words. The information paradox, a contradiction at the edge, 640 words. The holographic principle, Information on a surface, 700 words. Soft hair. The record on the horizon, 540 words. The no boundary proposal, before the beginning, 800 words. Holography at the origin of time, 600 words. The future of the universe. What time will bring, 650 words. What the dark carries a closing, 470 words.